Question number 4. So this one the question number 4 circuit diagram, and I have got the result also.
Mm-hmm.
That at 4 point. No, this one. Symbol test question number 4. Layout symbol. In layout, it's showing that middle one line is showing. But
Mm-hmm.
whenever I'm converting the symbol,
Okay. Yeah.
symbol
See, because it's so thin, that's why it's not visible. But it's there. If you zoom it out, you can zoom it out, it will still
is
be there.
I zoom it out, but it's not showing
But
also.
see, the thing is here you have to be very careful because
Okay,
you
sir.
cannot take the line as thin as you want. There is limitation in from the fabrication perspective, right? So
Okay.
I guess you can take as minimum 0.5 millimeter or so as the line width. Okay.
Okay.
So if you go below that, I don't know how much you have taken here. So
Actually,
maybe in the, yes.
in the symmetric, the exact value like I haven't got. That's why I did the like tuning. So by tuning, I got
That
that
is fine.
5.8.
Yes. How much? How much is the width?
Like,
Open the schematic ones and you will know. Okay, here, yes. How much is your width?
250.
Yeah.
0.024.
No, that is impossible to fabricate. Yes, you have
Okay.
to take at least 100 times more than that.
So
Okay. So,
instead of tuning this one, I have to tune another like
eh,
other one which is bigger. So
yeah, you can do anything. So that's
okay.
why, see, you should not tune blindly. Somebody asked few last class, right, that why we should learn about all this theory and all if you can just tune. So there is a limitation there. You cannot just take anything. Okay.
Okay.
So ideally you should not change the line width because line width represents the characteristic impedance of the line. You
Yes,
can
sir.
tune the length of the line. Okay. But generally width should be kept fixed.
Yes, sir. And
Only
sir,
like,
another,
yeah. Okay.
yes, sir. You can tell, sir.
Okay. So only in the worst case, if you are not getting anyhow, then only you should go. But I don't think like it should work normally because the normal filter design it is defined, right, and it works also normal case. So if you take a 50 ohm, I don't know which ohm you got, which line. So in case it does not come from the normal, the Kuroda transformation or something, you need to use a, defined transformation. I don't know how you converted them, so that you have to take care properly. You have to see if your conversion is correct or not.
Yes, but thing is that, sir, if we go with go with that circuit also, like go with that layout
Hmm.
session also,
Hmm.
like we are getting multiple frequency, like not only 5.8,
Hmm.
even
Hmm.
6.2 or 6.3 also we are getting that S11 and
Human ripples, huh?
yes,
Huh.
yes,
Yeah, that might be possible. That might be possible because because microstrip line they have periodicity, right? So it can come. Even if the design I have shown it was there, but I don't think it should be that close. I don't know. You
okay,
have to
sir.
see if you have done the design correctly or not.
Okay.
Okay,
And
you
sir,
just check once. Huh. Hmm. Hmm.
another question, assignment numbers 7 number question. Modify
Hmm.
the design 3 to band pass filter fifth order characteristics with FL like the frequency
Hmm.
band pass
Hmm.
should be 2.2 to 2.6.
Right.
So design 3 means question number here. So we have like we design equitable filter low pass filter at 5.8 giga like 46 gigahertz, but
Hmm.
here middle frequency which will be like what will be the middle frequency if you will design the band pass filter and the frequency range is 2.2 to 2.6.
Middle frequency will be obviously, between the lower and upper band, right?
2.4,
So,
okay.
so if you see the theory I have shown you before, so it just takes a transformation. Okay, omega naught by the delta omega.
Yes,
So you
sir.
have to
Yes.
transform. I did not mean literally you have to design that. I meant you have to start from a low pass filter design and then you have to move to a band pass or high pass.
Band pass.
Okay, that is the way it is. Okay, the
So
theory.
for that designing the low pass filter of question
Hmm,
number
hmm,
7, so we need
hmm.
to calculate we need to recalculate the inductor and capacitor for
No, nothing like that. See,
okay.
all the filter, low pass filter design, you take there is a table given in the book, right? That
Yes,
is
sir.
for
Yes, sir.
omega c equals 1. That means unity cutoff frequency. Okay.
Okay, sir.
If you, yeah, just go through it once, because it does not define a frequency. It is unity, and according to your required frequency, you have to take a normalization. Okay, you have to
Okay, sir.
multiply it. So you have
Okay,
to
sir.
do the same thing. Only the elements of the table that remain same, or the passive components remain same. Okay.
Okay, sir. Thank you.
Okay. Yes. Anybody else?
Yes, sir.
Hmm.
Sir, I have a question that in the given assignment, in which question you have given that just a schematic is needed.
Hmm.
So then just we have to show on the lumped component.
Yes. Yes. That is fine. Yes. You can show only with lumped components. Yes.
Okay. And sir, the next question is that question number 4 and 5. You have told the transmission line, low pass filter to transmission line coefficient. So
Right.
we have to convert the Kuroda's identity and Richards transformation, and
Yes.
after that, we have to convert in microstrip line fabrication.
Exactly, exactly. If you just see the previous videos, I have shown it also, right? How to do
Yes.
convert to microstep. Yes, exactly. You have to
Now,
do the same thing. Yes.
yes, but you have written that the transmission line. So that's why I have a doubt that you have shown the microstrip line fabrication converted in microstrip fabrication, but
Hmm.
transmission line is something different. That's why I am asking.
No, no, it's not defined, right? Microstrip line is a type of transmission line only. Okay, it's not
Okay,
different. Yeah.
okay, thank you.
Huh. Okay. Anybody else?
Hello.
Yes.
I made BPF, but it is different actually. Output is different actually.
Hmm, hmm, hmm. You mean bandpass filter or which one? I did not get.
Band pass filter only. I'm telling.
Uh-huh. So you are making for the assignment or the
Yeah, assignment only. Assignment
okay,
only.
okay. Uh, Not coming in the sense means what is not coming, right?
Graph is too gain is too more too less actually.
Okay, you are saying right, it's to one.
Shall I show my screen?
Yes, sure, sure. Somebody has asked about the substrate and all. I guess I have already mentioned, right? FR4 and substrate thickness also. So just read the assignment properly. It is.
For
Hmm.
schematic also substrate required.
Yes, yes. Schematic also is required, right? I mean, if you don't do from L and C, is not required. But the moment you
That is
shift to, exactly. Yes, yes.
like this. It is coming actually.
No, no, that's not correct. It
It's
should go close to zero. I doubt you
uh,
might have done some mistake there. Okay. It should not be that much.
I did everything.
You see, you start from a only third order of second order first. Okay. Then you move to fifth order, I suppose. First you go
Okay.
do, yeah, because I think you have taken a, yeah, initially only you have taken so complicated it so much. So first start from the simplest one and then move on to higher order. Okay. It
Okay.
should come. It should come. May not be that good. I mean, generally the roll up will be bad, but you should have a bandpass characteristics only. Yes.
Okay. Sure.
Hmm. Yes. Anybody else?
Sir,
Yes.
sir, I have one common doubt.
Mm-hmm.
Sir, for CPW, what is
Mm-hmm.
the spacing we have to choose, sir?
See, CPW, I am not teaching here, but if you see, they have a different design equation, just similar to microstrip line. So there is no specific, rule given that you have to take like this. Generally, what do we do? We use a line cal tool or ADS or CST, what we use. So similarly, if you see, they have option in ADS also for CST calculation or normal SIW calculation in different kind of transmission lines. So you have to follow those tools. Okay, it's not easy
Okay,
to calculate by pen and paper or just by some equation.
okay, sir.
Mhm. Okay. Okay. Anybody else?
Sir,
Yes.
sir, my
Yeah. Yeah.
doubt is that it's a general doubt.
Mm-hmm.
Sir, actually, there are analog design and RF design.
Mm-hmm.
How can we differentiate analog from RF, sir? Is it both are same or I have this doubt in my mind. Can you please clarify?
Okay. Okay. See, the thing is, what happens that, generally in the communication paradigm, okay, we have so many components in a transceiver chain, okay. So let's say there will be mixer, amplifier, filter, all these components, as well as there will be antenna and power divider, all these components, right? So generally in the communication, you can feed the signal from baseband. You give a baseband signal, and then they go through, the all the processings and all. Then it becomes analog, okay. So ultimately, what you feed to the circuit board is a what kind of signal? It will be the analog signal, because it comes from the carrier and all. Then it goes transmits through the antenna, right? So the moment you go to the carrier actual RF frequency signal, it becomes kind of like analog processing. But before that, all the baseband processing is done through in the digital mode. Okay. Yeah. Does it solve your doubt, or do you have any further
But
question? Uh,
RF, sir, I'm asking differentiation
hmm.
between RF and analog, sir. That
Yeah,
is
RF.
okay.
Yeah, you
That
see,
is
see,
okay.
even in RF also, if you have to see the applications, right? RF has many applications. If you see in the communication or radar, so it's not like, fixed that you can do only in the analog part or only in the digital part. You can do both also. But generally, what we mean by in the antenna perspective, we deal with the carrier signal, which is analog. Understand, right? The moment you generate a 4 gigahertz signal, that is an analog signal, because it can have any amplitude or phase. Okay, if you mean by
Yes,
that,
sir.
the which signal you are feeding, the base, the RF frequency signal, that is analog signal only.
Okay.
Okay.
Hello.
Yes.
If I have a inductor that is
Hmm.
not in the value that we cannot manufacture,
Mm-hmm. Yes.
then we can do windings now with that. What is that material? Mm, windings
Okay,
we
it's
don't
like
know.
spiral. Yes.
Spiral windings.
Uh-huh.
How many spiral windings we have to do? Any calculation is there for that?
No, it might be there, but I am not familiar. I have not done it. Okay. You have to find out yourself. Yes. It might be possible, but all these things, in the RF, it might be difficult. So if it will be best if you can do with microstrip line itself, like a shunted microstrip line. Okay.
Okay. Mhm.
Yeah. Only when the dimensions become, unrealizable, then only you have to move to lumped components. Then you don't have any other option. Yes.
According to the in our office also they are doing with enamel wire only actually. Their
Hmm.
calculation doing. I
Okay.
cannot ask them actually. That is a
Okay, 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 okay. So then, yeah, you have to find the closest component you can find in the market. Yeah, I don't know any specific, application for this spiral or something. Yeah, I have not done that spiral inductor. Yes.
okay.
Yeah. Okay, somebody has posted something in chat. Not getting periodic response. You are getting. Let me see. One is okay. Yeah, it kind of is okay, but no, after some frequency, your response again goes off, right? So I don't think it's correct, It should not be like this. Check once your calculation. Is this schematic calculation or microstrip line based calculation? I am not sure. Check your calculation once, or maybe first start with a third order filter, okay? Don't maybe directly jump to fifth order. First do it third order and then go to fifth order. Okay, so microstrip. Okay, you first do with third order, or if you can show your screen here, it will be better. Yeah, whoever has doubt, yes, speak. Pooja.
Hello, sir.
Yes.
Sir, for that question numbers, where you have asked about commensurate lines,
Mm-hmm.
you explained in the last lecture about that. That was from the third order it got derived. That example which you showed. I
Mm-hmm.
tried to follow the Poser book also. They have done that same thing and they have tried to explain. But the
Mm-hmm.
thing is, here we are doing that fifth order thing and we are
Mm-hmm.
converting it to the commensurate lines. So where
Okay.
there are two first and last inductance will be same and the middle inductance will be different. So I
Mm-hmm.
calculated accordingly for all of those values, but
Mm-hmm.
that n square value there we are
Mm-hmm.
adding also line for that n square in the first and end portion. So
Mm-hmm.
for the middle inductance, do we have to do like that? That I'm confused because in general, what we have to do, can you explain a bit so that we can know that
I
whenever
mean,
it is
if you show your screen or something, what you have done, you will, or do you want me to go to the theory once again?
actually, so my laptop audio is not working. So that's why I'm attending from phone now.
Mm-hmm. Okay, okay, I'll try to open that theory once again. Let me see.
Only you can explain in the general perspective if whatever order we are getting, fifth
Mm-hmm.
order or sixth order, then what we have to do, because we have to calculate first n square. So accordingly that n square, your inductance value, you can do the commensurate line transformations. Then you have
Mm-hmm.
pre-normalize it, then you have to do.
Mm-hmm.
That is the thing I'm not getting, because third order I got explained properly where only
Mm-hmm.
two inductance and for low
No,
pass will be one
i-
capacitor.
see, the thing is, it does not, the microstrip line implementation does not depend on order at all, right? I mean, why I understand why you have a doubt there, because it just depends on the what you get. Okay. I mean, your theory. It's not, just a minute. So let me see. So you are, let's say you are talking about, yeah, let's say here, right? So here you see there is a inductor this side and that side, right? And in between
Yes, sir.
capacitor.
Yes.
So we are replacing
Yeah.
inductor and capacitor as it is, right? What is the problem here? If you have, this is third order, you have more, so there will be two more inductor and capacitor. So you will just replace everything by one, right?
No, 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 sir. I'm not talking
Hmm.
about the inductors capacitor. You just
Hmm.
1 minute, 1 minute. So there
Hmm.
is a slide where you have calculated n square is equal to one plus
Hmm.
one
Hmm.
minus one plus z2
Z2
by
by
z1.
Z1. Ha ha ha.
There only that one n square value whatever we will get now. For an
Hmm. Hmm.
example, in this example you got 1.299. That
Hmm.
also is coming as a transmission line. That is a problem. Like that I'm asking. Like because
Okay, you are saying in between what to take, huh?
that in between wala inductor, do we have to also consider n square for that? Because n square is coming from the values, because first we have to take z is equal to l. Then that L we are calculating from that Z is equal to L, that inductance value is getting convert into first n square Z for inductors and 1 by n square Z, like that we are doing.
Z
There
is
only
L means what is L?
L means inductance, sorry. Like
No.
for
Yeah, that means the characteristic impedance of that line. Are you
yeah,
meaning
yeah,
that?
yeah, that
Yeah,
only, yeah.
it
First
must be
we are
see.
considering L as the characteristic impedance, then we are
Mm-hmm.
converting it to.
Yeah, actually, you have to take what is nearest characteristic impedance you have. Which one is the connected line? Okay, it's not like the Z naught. See how it goes here. This Z1 is the connected line to this capacitor. So then closest inductor will be this. Okay. So you have to see which your capacitor, inductor, whatever, which line is it connected to, which people,
Actually, which is connected to the end port and first port and end port.
Yes, yes.
Oh.
Actually, yeah, I will open the PPT also once. Let me open that.
Sir, you can show that example there only I can get.
Understand, understand. I guess this one you are talking about? This
Yes,
only
yes,
here?
yes,
Yeah.
sir. Yeah, that one only.
So see, instead of this, if you have multiple inductor and capacitor, so you have to see here, this is the picture, right? I mean, I think, yeah, let me take the
Yes, sir. You can see
laser.
the last picture, sir, in
See
the
this,
third picture.
yeah, exactly. See here. Here you have a capacitor, I mean inductor here, which is the shunted stub, which is replaced by a open stub, that is capacitor. So the Z2 line is right of the inductor here, right? See, this is the inductor and the
Yes.
line here, okay? I mean, okay,
Huh.
okay, I understand. Here, see, it is opposite. Line is here. So it has to be just symmetric. Line this side or that side, it depending on that, the capacitor here, the open circuit in orientation will change. Here you see, the line is first and then inductor. Okay. So that how did it came here? Here you see. So first open circuit, then the line. Okay, here you see. Which side was the center stub? In that one, you have KZ1 line. Understand? And here the line was there, now here it became open stub. So it just changed position.
Okay.
Okay, so that means you have to take first line and then inductor. Yeah, but you can do the otherwise also. So you have to just see which is convenient to use, because ultimately you have to see fabrication, right? So which one is possible to fabricate? Your from layout, which one is okay? You can take either ways, but here it was feasible because you could here we could add a extra line because of port, so it was okay.
Okay, so are you saying me that can you see look into that number 3 second Kuroda identity picture where
Yes.
that is Z naught is equal to 1.29 and that is actually value of n square. So
That is
and that
from n square. Yes, yes, yes.
yeah, that n square is coming from 1 plus Z2 by Z1 and here
Yes.
Z1 will be considered as that 3.48 3.3487. So that was the inductance value which we got.
Right.
Yeah, so I am asking that for that inductance, this one extra line of impedance line, which is you got as 1.299 as at the first, and at the last you can see. So if in
Right.
the middle I am having one more inductance, which is different in comparison to these two. So for that n square will be different. That
N
n
square will
square,
be different. Yeah.
yeah. So there will be two n square values. So what should I do in that case? That's I'm asking. That's why, you got me right. What I'm trying to
No,
say,
this
sir.
2n square thing I did not understand. Why there will be 2n square? I mean, there will be
Yeah,
different values. Yeah, it won't be same, right? That is what you are meaning.
sir, we
In,
have done fifth order, na? So there will be three inductors, and first and last will be same.
Yeah. The values will change. Okay. The first and last will be same because they are, if you see actually, all the G
Huh.
components are also symmetric.
Symmetric. Yeah, that's
Yes,
why.
it
Huh.
will be symmetric. Yes.
Yeah, that's
Symmetric
why
with
first
respect
and
to the
last
middle.
is. Huh.
Yes.
So the first and last n square is same, but for middle the n square will be different. So the
Different, right? Yes.
we have to also extend two more extra lines from the middle for that middle inductor. That I'm asking.
Yeah. Actually, it's needed because that's why it's fifth order, right? Yes.
So
Yeah. So
if we
that's
are
why. Yeah. Yes.
if we are extending two extra lines from the middle, do it has to be like beside the two extra lines or one extra line? So because here for every each inductor one extra line, so you can see, not like it is not two lines for
Yeah.
each.
Understand. Yes. You have to then add two line. Yes.
So I have to check with the S11 and S21 response, then only I can see, right?
Right. Yes.
Because
Yeah.
S11 and S21 now it is coming really weird. It is not coming
I
properly.
think you have not added these extra lines.
I
Unless
have
you add
added,
the
sir. I
no,
have
but
added.
you
Actually,
cannot just add extra lines in between. The
yeah, the
calculations you have to do
position it
properly.
has to be, yeah.
Yeah, exactly. Yes. Okay.
So that's
So
why,
that is the part of assignment you have to do, and then only you will earn. Okay. Yeah. Okay.
yeah. So
Yeah.
I thought I
Okay.
made something wrong
No,
because I
no, no,
do not
nothing
have to
wrong.
add.
See, that's why I gave fifth order. So you will have to do, extra additional things. Otherwise, just like copy paste from here, right?
Yeah.
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 Okay. Yeah.
Okay,
Just
okay,
or
sir.
maybe you can look into additional examples also, fifth other examples. You just search in, Chrome or nowadays ChatGPT. You will get thousands of examples. Fifth order filter, definitely there will be examples. Look into that. Mm.
Yeah. I'll give it a bit of time.
Ah.
I just wanted to know that whether I did something
No,
wrong or.
no, no, that is fine. The point what you raised is correct. Yes. You have to just, study a little bit more. Okay.
Sir, can I ask one more question? It's a basic question. I'm
Yes.
working in antenna, sir.
Mm-hmm.
I have to also give equivalent circuit model for each designs, whatever I'm doing. And my
Mm-hmm.
background is MSc Physics, actually. So,
Okay.
can you tell me that if any design I'm doing, whatever
Mm-hmm.
design it is, 3D model I am doing with HFSS 3D modeling thing and only. So, if I have to
Mm-hmm.
convert into LCR component, like
Mm-hmm.
equivalent circuit in the lumped component form.
Mm-hmm.
Do the way we did in the one you have given that commensurate line or that where the transformation is taking place, do we have to
Mm.
follow in the reverse order like that it has to be done, or is there anything different we have to do?
You are saying from microstrip line to L, circuit
Yes,
equivalent.
sir. Because if you're doing a
Uh,
patch antenna also, that is nothing but LRC
mm-hmm.
component combination only.
Mm-hmm. No,
So,
no. See now, for a antenna, it does not behave like a normal circuit, right? It is a resonator. Okay. So
yeah, it is
basically, you will
resonated. Yeah.
have the RLC components there. Okay. So for that, I will suggest you follow the normal basic Balani's book. Okay. They have given how to represent it as L and C. Or if you want more fundamental analysis, I will suggest you go into the microstrip line handbook by this Bal, Garg, and Bharatia. Okay, that is even better.
Sir,
Microstrip line handbook. Yes.
so representation, I know, sir. I just
Mm-hmm.
want to know the value, sir. Like values, what are the exact values that has to be used? We can do it and trial and seeing the S11 response also, where the resonance
Mm-hmm.
is coming. That is one way to do. But I don't know whether there is a correct way to do like that.
See, if I also don't have much expertise on that. If I have seen generally the load impedance and all, you can get a value, but
Yeah, that is
most of those some of these you can calculate for a basic antenna. Okay, the moment it becomes complicated, it does not match with the equations. So then you have to go to the CST and hit and trial, the same what you said. Okay,
okay,
so
okay,
yeah, it's like that only. Yeah.
okay, sir. Okay, sir. Okay.
Hmm.
Thank you, sir.
Okay. Okay, so I think today now I will start class. Okay. No. So today we'll start from the active circuit design, and we'll cover the RF diodes, mainly pin diodes, and then we'll go into how to use it for phase shifter circuits. Okay.
Just a second, Saurav, like before starting with, like
Hmm.
I have one basic doubt from the last
Hmm.
assignment of what you
Okay.
have given,
Mm-hmm.
like specifically with respect to the design of equi-ripple fifth order low pass filter.
Okay. Yes.
So like we can take two approaches, like either series, starting with series L or
L.
shunt
Mm-hmm.
capacitance. So suppose if I'm following series L, low,
Mm-hmm.
so for the fifth order, I think we have G0, G1, G2, and so on up to G6, right?
Mm-hmm. Right.
So the G6 coefficient from the table, I think it is corresponding to like our load impedance only.
Mm-hmm. Right.
So in that case, like as I see the impedance transformation there, in that case we have kind of for impedance scaling, I could see the ZL dash is a multiplication of R naught with ZL, right?
Mm-hmm.
So in
Right.
that case,
Yes.
our ZL will be initially 50 and even R naught is 50.
Mm-hmm. Okay.
So if we multiply those two things, we'll be getting like a huge impedance for that line, like 50 into 50, 2500. So is it a right, means like, am I understanding it right way
Yeah, no, no,
or?
no. Come again. What is the? I think it will be in the one will be in the denominator, another in the numerator, right?
No, 1 second. I'll just open that. Maybe actually last week's session I couldn't attend. Uh, but so I'm following that Poser book only. Maybe I'll just
But
share
okay,
my
but
screen.
I have uploaded the videos, right? You can see it.
Yeah, I'll go through that also. Like maybe just quickly, I'll just
Mhm.
present my screen so that we
Mhm.
can. Are you able to see my screen?
Yes, yes.
Yeah, actually, this is the impedance and frequency scaling section, and I could see RL dash is a multiplication of R naught and RL. And from this table for the fifth order filter, we see the coefficient G6 is 1. And
Yes.
also, as I have gone through this, the text here, because it is 1, I think it is a kind of like our load impedance. And this is as this is a normalized coefficient, we have to follow the impedance scaling as per this. Like RL dash should be multiplication of R naught and RL.
Yes.
And as I see, R naught is 50. And even RL also is 50 or like
No, it will
like
be 1, right? RL comes from your end, the end coefficient. If you go to
from this
the
coefficient.
circuit, circuit schematic, go there in the previous
Okay.
page. I think it will be in the previous page.
Yeah, here it is.
They have a circuit given, right? Yes. So see, what is the last component? Gn minus 1. That is only your load, right? The
Gn
last
plus 1.
component.
Yeah, this should be
Exactly.
the
That is
load.
your load.
Okay,
Yes.
okay. So that is 1 only.
Yes, yes.
Okay, okay. Yeah, that's what I had a small doubt. Okay, okay, fine then.
Yes,
So
yes.
now the next part of the assignment is like just we have to convert all these lumped elements to microstrip lines. Correct, no?
Right, right, right.
Okay, okay, yeah. And as I can see, you have mentioned like last date is 16th. I'll try to finish it off by tomorrow, but if
No,
possible,
no, yeah,
can I?
I will extend it for another week. Okay.
Okay, okay.
Still last next week also you can do till next weekend.
Okay, okay, okay. Yeah.
Yeah,
Thanks,
yeah.
sir.
Yeah, okay. Okay, okay. So it's good that you guys are trying really hard. So yeah, actually that is what I wanted so that you also learn, do it yourself and learn. Okay.
Right.
So now let me go into the next class. Okay. So why there is a need for active circuits? Okay. That is the first question in our RF. So let's say many of our circuits in the RF, we need reconfigurability, right? Let's say we want to see reconfigure the phase or amplitude or even frequency. All of this we can tune, or nowadays it may be required. But let's say you see a lot of literature like with reconfigurable pattern or reconfigurable polarization. All these things are there. So how do you make it reconfigurable, right? So for that, you need to have a component which can switch or shift the amplitude or phase. Okay. So that is where these active circuits come into use. Okay. So today we'll first start with the diodes and then we'll see like what are the uses for just switches made of simple diodes, how we can use it. Okay. And for reference, you can look into Poser book. And there is another book from this Dr. Bal and Bharatia. I think it is microwave integrated circuit, something like that. So that book also is very good. You can follow. Okay. Otherwise, the Pojar is always good. They have very concise and cover is they covered the theory also in a concise way. Okay. So generally, from talking about diodes, the which is mostly used is pin diodes. Okay. So why the pin diodes has such a importance in our switching, RF switching, is why is that over the normal PN diodes? Okay. So in case of pin diodes, what happens? We have a intrinsic region between the P and the N junction, N region. Okay. So how it helps that it reduces the junction capacitance. So the first question is, why junction capacitance reduction is necessary? If you see in the normal diodes, we have a junction between the normal P and N, right? So that is why you have the same amount of charge, but the area is very less. Okay, the area over the depletion region area is quite less, and the same charges is concentrated over there. That makes it very high capacitance, very high junction capacitance in the forward bias. Okay, now just by inserting this I region or the intrinsic region, what happens? You distribute the same amount of junction charges over a larger area. Okay, that is why this junction capacitance reduces drastically compared to the normal PN diode. So now what are the advantages of this? So the moment this capacitance reduces, you can use it for higher switching speed. Okay, this makes it feasible for using very high switching compared to the normal diodes. And also because of the because the capacitance reduces, it also reduces the isolation, it improves the isolation as well as reduces the insertion loss. Now we'll come to that how it affects those because of the capacitance value. Now as you see here, the diode as it fabricated, it makes the geometry itself, it makes the difference. Okay, so as you see, the operation is quite similar to normal P and N diode. You see there is a normal forward region where the after threshold the current increases drastically. So you have a resistance there, forward resistance. But in the backside or the reverse region, you have a reverse bias as well as you will also have some capacitance coming, reverse capacitance. Okay. So because you increase this, the region of the, the intrinsic region, the charges may not recombine quickly. So that means there will be some charges stored, and that reduces the resistivity. Okay, and because obviously the depletion region widens, you will have a lower junction capacitance. That makes it suitable for high switching. Okay, so yeah, so starting from here, yeah, do you have any doubt here? What makes PIN diode so attractive for RF switching? Do you understand why the insertion of this, intrinsic region, how it helps? Okay, that was the point of this.
So basically, I think the reverse recovery will be removed in case of this pin diodes compared to a normal PN diode.
No, not reverse recovery. If you see this junction capacitance and all, they come more into effect in forward bias. Okay, so that is
Okay.
what it is more important in the forward bias itself, not in the reverse bias. Reverse bias, it will act as the cutoff will happen and it will like it'll go to the signal will not flow. But when the signal flows through the diode, then only the concept comes how fast you can do the switching. Okay, so that will depend on the capacitance form in the junction, right? Okay,
Yeah.
so that is the distinction you should make here. Reverse always, it is reverse for normal diode also, but for the forward bias case only, it acts differently. Okay.
It
Okay.
is, you can put it other way, that is minimum threshold, minimum threshold where it goes more than minimum threshold, it turns on.
No, the threshold might be similar. It does not depend on that, but more it comes from the capacitance or the junction capacitance, which affects the switching performance. Okay, but yeah, we'll go more into the device parameters into next slide. But till now, is the junction capacitance part clear? You see the picture here in the right side picture. See how the capacitance is getting distributed over the intrinsic region in between the P and N. So if you remove the I region, what will happen? There will be a very thin region where the same amount of junction charges will be formed. And because this thin region has a very low area, how do we define the capacitance? It will be, depth of the depletion region as well as it will depend on the area, right? Because the depth reduces so much, it will increase.
No, even in that case, like if we are removing completely the intrinsic region, maybe we are also removing that area part also. Like
Yeah. Uh-huh.
now we see the uh, adjacent means like locations in like means like in the location where
Mm-hmm.
more negative charges are concentrated to
Mm-hmm.
the a region where more positive charges are concentrated. That is like
Hmm.
from P to N.
No,
So
no.
in
See
between
the
that region,
no, diode cross section remains same. We are not changing the cross section, right?
okay, yeah, cross section will remain same.
Remains same. Yes,
No,
yes.
now actually my doubt here is like the intrinsic reason, whatever it is mentioned with I letter in that. So
Mm-hmm.
you're like removing that reason completely, or
No, no,
how
I am
actually I
not
didn't get that.
removing. I am not removing it. That is
Okay,
the way the pin diode is represented. And if you see a normal PN diode, you don't have any intrinsic region, right? That is how the difference is.
that's what like for a normal PN diode, we don't have any intrinsic
Ah,
reason.
exactly. So my point is why this intrinsic region, how it helps for the switching
Can you
case. Yeah.
just explain once again? Like actually, like
Yeah,
how the
yeah, that I am saying the same amount of junction charges because of the forward biasing. When what happens, it gets, it gets distributed over a wide intrinsic region. Over the whole region, it gets distributed. Okay, so that's why the capacitance, junction capacitance reduced
Mhm,
compared to the
okay.
normal PN diode. Yeah, so that means the it reduces the capacitance, and basically that will define your switching speed as well as isolation and insertion, everything as a switch. Okay.
Yeah, yeah, understood. Now I got it.
Yeah.
Yes, thank you.
Okay. Okay. So now next, so how do we define and what are the parameters, right? So generally what happens, so if you want to use this simple pin diode as a switch, what will happen? We will fix it for a two defined biasing condition, right? Let's say forward and reverse bias. And by applying this control voltage, we can just switch between these two states, and that will define like how the circuit will behave in and generally the power can go as high as around 100 milliwatts and so. Okay. So how do we define a diode like this? It will be like one capacitor in the parallel and a and another resistance. Resistance and capacitance parallel. What is this resistance? This is the forward or reverse resistance, and the capacitance comes from the junction capacitance. Okay. So now if you see here, this what is written in the green is for the forward bias case. So what happens there? Let's say all this let's say for a 1 gigahertz frequency, you have let's say one junction capacitance of 1 picofarad. Okay, so you have a inductance or the impedance because of the capacitor is around 160 ohm for 1 gigahertz, and generally your forward resistance is around 0.5 ohm to let's say around 2 ohm. It will be very less. Okay, so because they are in parallel, so what will happen? Which has the lesser value or the lower value, that will have the priority, right? So it will act in the forward, it will act almost as a resistance connected in the forward bias. So 0.5 ohm or very less ohm. So that means it gives a direct path for the signal with very less impedance. But when you go to the reverse bias, what will happen? You have the same capacitor, and the capacitance value will maybe change, but what it mainly changes is the reverse resistance. It will be very high now. When the diode goes to the reverse bias, obviously you will have a here let's say 20 kilo ohm, but it can go as high as to 1 mega ohm also. If you have a very good pin diode, your reverse resistance might be around 1 mega ohm. Okay, so what will happen there? There it will act, let's say around because then you have parallel one resistance as well as a capacitance. Then it will mainly depend on the capacitance because the impedance coming from the capacitance itself is less. Okay, and in as you know in the parallel connection which has a lesser value, that dominates. So that's why in the series connection you can represent this like a normal resistance, and in the parallel connection you can determine you can define it as a normal capacitance, right? That will be determined by your capacitance. And if you see here, if your capacitance value reduces, your impedance coming from the capacitance, the contribution due to capacitance, it increases, right? So that means it will become like it will give a more isolation. That means it will ensure there is a better impedance in the path of signal. So that's why it is required that you reduce this capacitance also, junction capacitance. Do you see the point here? If you reduce the CGA here, in the reverse case, the impedance contribution from the capacitance, it increases. So that will ensure that you will have a better isolation in the diode off condition. Okay, so that is the two cases, one case and off case. In the simplest schematic you can have for a pin diode, a resistance connected in parallel with a junction capacitance. So if you see a data sheet, you will have both of these given. The CT will be the thermal or junction capacitance as well as the resistance. Now there will be some other components also. We will be coming to that. And before that, there is also figure of merit for judging how best is or how good is the diode. So you generally take as a ratio of R on to C off. Okay. In the on condition, how much resistance it can give, to the off condition, how much capacitance is given. Okay. This is taken sometimes as a figure of merit. Okay. So before I move up, do you have any doubt here? Okay. So let's see now.
Sir,
Yeah.
so in the reverse bias, the value of resistance will be negligible and only the capacitance will be there. Is it correct? And capacitance.
No, you tell me. No, you see here, it is how it is defined. The circuit is in parallel, right? If you connect two impedances is parallel, which one dominates? How do you take the equivalent impedance of two parallel connections, parallel resistances, let's say? How do you take it?
So the one which has the lower value out
Exactly.
of the.
Yes, that is what happening here. Yes.
So it is basically an open circuit.
Yeah, that is how it should be, right? If you want it to be switch off, it should be open, right?
Like in the RF, when we pass the RF signal, so capacitance is used to block the RF signal and inductor is used to block
No.
signal.
Capacitance is not blocking the RF signal. You are having a very high impedance in the line. What is ZCR? ZCR is the impedance given from the capacitor, is the contributed by the capacitor. If you have a very high impedance line in your signal path, how can the signal move? It cannot move. It's just as if you give a DC signal, it will not move. It's same to that also. If you place a very high impedance component in your signal path, signal will not flow. Okay, it's not because of capacitor or inductor or anything. It is because of the total impedance contributed by the components. This is if you have to, you have to remember that these are the equivalent circuit. This is not like, we are analyzing like this.
Yeah. So we are just analyzing the green one for forward bias.
Yeah,
the equivalent is equal to resistor, and for
right,
inverse
which
bias
will
is
be
equal to-
dominating. Yes,
Yeah,
right. Yes. Okay,
Okay.
and we'll come to that. Like, it is not limited to this. There will be many other components also. We'll go to there. Okay. Yeah. Okay. So now next
as
is
per this one
we'll
doubt, like
come
the
to
figure
doubts
of
later. Okay. Yeah. So now, yeah. What are the other characteristics of pin diode? Let's see. So for a pin diode, we have RF resistance. Obviously, it will be controlled by the current, because the moment you change the current, there will be because the voltage component, the voltage drop remains same, so resistance will change. Okay, so you see generally the resistance will reduce as you increase the current. And now you can also increase the DC bias. So because you are giving the DC bias, so adjusting the current, you can adjust the RF resistance of the diode. So when the diode is biased off, that means it is switched off. So there will be very high impedance approximating an open circuit. So it behaves like an open circuit because of the very high impedance given by the switched off diode. Okay. so that ensures there is no signal flow. So that's why it acts like a switch. Okay. Now, the junction capacitance, it is represented by CJ. This formula you might know from your basic semiconductor device circuits, represented by epsilon A by W, right? The epsilon is the permittivity. It will be in silicon around 11, if I remember correctly. And W is the width of the depletion layer. Now, there is a very vital component which is called junction relaxation frequency. Okay. So, which is defined by FD given by 1 over 2 pi rho epsilon. Okay. So, what is this rho? Rho is the resistivity of I region. I means the intrinsic region in the pin diode. And epsilon is again is the dielectric constant of the region. So, now why this relaxation frequency is important? So, what happens that this relaxation comes from the, if you have heard, I don't know, that, there is some phenomena called dielectric relaxation. If you pass a high frequency signal through a dielectric material, so if you see the dielectricity comes in a material because of polarization, right? Now the moment if you pass a high frequency signal through it, the polarization of the charges will change very quickly. Okay, it will try to shift it, but it will take some time to come back to its original position. Okay, to get back to the equilibrium distribution of the charges. If it does not happen, then it will stop behaving like a dielectric itself. Okay. So that is called dielectric relaxation effect. And the time it takes to come back to the main dielectric orientation of the charges is called dielectric relaxation time. So if you see in the junction also, what we have mainly the orientation of charges in a particular manner. Okay. So if you pass a very high frequency signal, so it behaves like a one way. But if you pass a very low frequency signal, so then what happens? It will keep on changing the orientation of the charges so much. Then what happens? It will act like a varactor diode then. Okay. So it says if your frequency is very much less than the FD or the junction relaxation frequency, then it will not act like a normal capacitor. Okay. So then it starts behaving like a the varactor diode. But because based on how much capacitance you can get on that condition, it will stop behaving like a pin diode. So generally, I was looking into data sheets. It says that it happens like around megahertz frequency. Okay, so generally this relaxation frequency come at a frequency range of around 20 megahertz. Although your pin diode can work in a gigahertz range, you cannot use it for a very low frequency. Okay, like a megahertz range. What happens in that case? The moment you go below this relaxation frequency, it starts behaving like a varactor diode. Okay, you can't use it as a switch, normal pin diode switch. So that is one very interesting characteristics from a pin diode, which comes from its semiconductor characteristics. But there is another component which is called transit frequency. Now, another thing is this junction relaxation frequency, obviously it comes from your diode when it is in forward bias, because junction capacitance mainly comes in the forward bias condition. Okay, so it takes effect in the forward bias condition. Now in the reverse bias condition of the pin diode, which is mainly important, is something called transit time frequency. So what is that? So now what happens? Your normal resistance you can define as a W, your depletion layer width as in this equation if you see, and this charge, total charge, stored charge, it can be defined as the forward current as well as the transit time. Okay, so what is this transit time? It means what is the recombination time or the carrier lifetime required. So that defines the how much resistance you get in the forward region. Okay, so I think I have told you in the other way. So in this transit time frequency is applicable for the forward bias case, and in the reverse case it applicable for the otherwise the relaxation time. Okay. So now what happens? Because your stored charge in the forward region, it determines your forward resistance, RS. Okay. So that's why if you see here, your RS or forward resistance is inversely proportional to forward current, IF. Okay. So the plot here, it shows your forward resistance with respect to the current, forward current. As you see, like as we are discussing before, if you increase your current, biasing current, the resistance decreases. So this is the reason behind this. You can actually, calculate from your parameters how much resistance you can get from your diode, okay, using this formula. So now what happens? You cannot use this diode in independently in all the frequencies. So here also you have a minimum threshold in the frequency. In the upper band, you can use in gigahertz range, but in the lower band also you have a limitation there for pin diode use. Okay, so that frequency here it is called the transit time frequency, and the expression is this equation 1300 divided by omega square. So this also it comes around 10 megahertz or so range, or 1 megahertz to 10 megahertz range. So that means below this frequency you cannot use it as a pin diode. So what happens below this frequency? What happens? It behaves like a normal PN diode. Okay, the PN diode ceases to act like a normal PN diode and it behaves like a PN junction diode. Okay, and that's why. So normal PN diode, if you remember, it is used as a rectifier, right? So in the forward bias, it gives some characteristics, and the reverse bias, it gives some other characteristics. So generally, it behaves like a rectifier, but that is not the switch we are looking for. So if you actually see, so this transit frequency as well as the relaxation frequency, these two puts a lower threshold on the use of a pin diode. Okay, you cannot use a pin diode up to DC. Okay, for switching, you can use up to, let's say, 20 to 50 megahertz. But in the higher frequency, you can go, let's say, into up to gigahertz, or very high frequency you can use. So yeah, do you understand these things? Yes. Do you have any doubt here? Okay. So if not, now we'll move to the equivalent circuit. Yes, yes.
So, as you said, like pin diodes, we cannot use for lower frequencies, and for the higher frequencies, what is the maximum?
Yeah, that I'm coming to next. Yes, yes.
Okay.
Yeah, higher threshold is also there. That I'm coming to. Yes, yeah. So yeah, now you see what happens. Just like any packaged material or any packaged device, here also we generally have a packaged device, right? So that will lead to the equivalent circuit of the packaging or the lead inductance, lead resistance, as well as the packaging capacitance. Okay. So now you see these values will be very less actually. Okay, LS and RS, it will be, let's say, very, compared to the normal capacitance or resistance, it will be very low value. So what happens? So at very high frequencies, let's say 50 gigahertz or 100 gigahertz, these components now will start dominating. Okay. So then what will happen? Because a capacitance and inductance in series or parallel, it will behave like a resonant or tank circuit, right? If you remember from your circuit classes, it behaves like a resonator or tank circuit. So at very high frequencies, it does not behave like a switch, but it starts behaving like a normal resonator. So you won't have, so that puts a threshold there. And that higher threshold comes from your parasitic values of the package device. If you see any data sheet that comes with, the stray capacitance and inductance, all this they will mention. Okay, that will put a higher threshold. So now what happens? The attenuation you can define for any switch in terms of the inductance sorry, not inductance, the impedance, equivalent impedance coming from this equivalent circuit. So if you determine this, it will give you total R plus JX, resistance as well as reactance. Okay. So now how we define this, the insertion loss, insertion loss and isolation, these are the two important parameters how we characterize the switch. How do we define that? If you connect this switch to a device, that means a source matched to a 50 ohm load, and this your device is also has to be matched to another load on the other side. So what will happen? So either if you see the here, this is the book itself. So you have a source and you have a Z naught, which is the characteristic impedance of the source, and it is matched to a characteristic impedance of load Z naught. If your switch is on, then the whole signal has to be passed to this. You will get a some signal VL in that case. And if you don't have the bias, the switch at all, then you have another voltage here. So now in the switch on and off case, how you define it is this ratio. This is called the isolation loss. It gives you the ratio of the V naught divided by VL. Okay. So V naught is what you give when your the signal is, I mean the device is not there at all. In that case, how much signal you get in that the load. If you just remove the switch here, so ideally you will get here V naught only, right? Because it's matched completely. Now the moment you put a device here, it will act as an on and off condition. So you will have two defined isolation loss or insertion loss, on and off. So for that, what you get in the load VL, so that ratio will define the VL and V naught will define the insertion loss. Okay. Now we have to remember this loss when we say it has to be positive. That's why this minus sign come. Okay. The moment we talk about a loss, it has to be positive. And the moment it works as a open circuit, that means the switch acts like, switch off. Then we call this insertion loss as the isolation. In the off case, the signal should not ideally pass, right? So we generally, you should have a 20 dB or 30 dB isolation between the input and output side. So is the definition clear? So that is how it is defined. Now, how do we, get this VL and V naught ratio? Okay, that if you see from here, it is you take from here this normal circuit. It comes from the ratio of the source and load characteristics as well as the ZD comes from the device. Now, how your device impedance connects, that is what you get from your equivalent circuit. If you take that, finally it comes to this. This inserts forward bias case, the insertion loss, it behaves like this. So in the forward path, you have RS plus RJ, that is, the stray resistance as well as your junction resistance, and then divided by 2 Z naught. Z naught is the source and the load characteristic impedance. Okay. And in the reverse bias, you will have the isolation. That means the signal should not pass through it. So that is defined through, if you just, see in this equation, it behaves like the capacitance, right? We have replaced the equivalent circuit with the capacitance. So only the capacitive component, if you see, it becomes like 1 over 2 omega C J naught G 0. Okay. So that is what happens. Because that is how it behaves like a isolation circuit here. So the isolation will be defined by the inductance or capacitance in the circuit. In the forward case, the insertion loss will be defined by the total resistance in the circuit. Okay, so that is how we define it. The two important characteristics of any switch, it is defined as insertion loss and isolation. Okay, so do you have any doubt here? Okay, so I think, yeah, we'll move it, maybe take questions at the end because of time. Okay, so ideally what will happen, because it's a switch and it has 2 ports, right? So we will have a scattering matrix or S parameter matrix. This is as usually we do, right? So what will happen? S11 and S22 should be 0 as usual. It should be matched, and S21 and S11 should be S21 and S12 should be 1, right? Because ideally the whole signal should pass with some phase delay. Let's say that's why this theta comes. Now what happened, so it shows like two different conditions. One in the diode on case, another in the diode off case. So what happens? In the on case, the whole signal passes with some minute attenuation. So that is given by the insertion loss. This V out by V in, the ratio. Okay. In is what you pass and V out what you get. In the switch off case, the signal should be mostly attenuated. And that is, judged by how good it is attenuated is judged by the condition or term isolation. Again, the ratio remains same. So ideally, we should have a very good switch which will give, maximize the isolation and minimize the insertion loss. Okay. So it's like a, short circuit or open circuit, but that you don't have for a real circuit because there will be a lot of components and all. But that is how, it should be, maximize one and minimize the other one. Okay. So now what are the uses of different RF switches? So generally what we want? We want to have multiple paths in the RF, want to switch up one and switch on the other one, right? So let's take a simple case of a transceiver circuit in communication, where we have a single antenna connected to one transmitter as well as one receiver, right? Generally, let's say even in our, in our mobile phone also, right? We have, let's say, one antenna and there will be both transmitter and receiver. We want to, get the signal as well as transmit signal. So if both of them are connected to the same antenna, but then what to be done? We have to switch between this point, node 1 and node 2. If you see the picture below at the end, so we have to either switch between the transmitter and receiver, right? From the single antenna. Because, it's not a full duplex circuit, okay? So that's why this is called a duplexer. You want to switch between these two states, transmit and receive. So here we will use a switch, okay? Like the switch we have seen before. Now there can be various different type of switches. One can be SPST switch or SPDT switch. Okay. Okay. By the way, there is another use. Let's say in a radar. Okay. Okay. In a radar scenario, you want to transmit as well as receive. Okay. You want to transmit a very high signal through the antenna, and then you want to receive the reflection or the echo, right? So you need a very high isolation between the switch also. Why? Because your transmit signal will be always very high signal, high powered signal. And what you receive, the echo, it will be generally, very much attenuated signal, which will be even, milliwatts or nanowatts, okay? So microwatts. So that's why, yeah, high isolation is required because otherwise it will interfere each other, okay? Now coming back to the different prototypes of switches. So very simplest switch is SPST. Okay, single pole, single throw. That means you can have switch on condition, the switch, the diode signal will flow, or the off condition, the signal will not flow. Okay, so that's why it's called single pole and single throw. But now, even in this simplest switch, you can have two different combination. One is a series switch, and there is a shunt switch. So what is series switch? The first case, if you see, you can just put a switch between two microstrip line. Okay, you can put a pin diode here between two microstrip line. In the other case, what happened? Instead of putting between the lines, you can put in a, as a shunt, just like a shunted stub, you can put a shunt switch to a microstrip line. That is called a shunt switch. Now, what are the other things we have to consider here? So, if you remember, the diode acts as a switch only when you bias them, right? And you have to switch the bias between forward and reverse. So then only it will act as a switch. You can know if you just put a pin diode and done with it, it does not act. So the moment you have to bring a biasing, you have to ensure a lot of things. That you have to ensure DC isolation as well as RF isolation. Your bias line should not be affected by the RF signal, as well as your RF path of the signal should not be affected by the DC bias signal, right? That is what you want. So that's why we need other components here. we need blocking components. What will happen? We need a DC biasing component, DC blocking component. So what is the DC blocking component? Is a capacitance. And what is the RF blocking component? That is called RF choke or a RF inductor. So just for facilitating this biasing of the diode, you need multiple components. So it will be either your capacitor or inductor or RF choke. Those also you have to now put to make a switch. Okay, so here if you see in the picture, we have shown just a cut or the green cuts. It shows like a capacitor. Okay, to block the DC here, so that the DC or the biasing and the red lines are the DC signal which will be required for biasing the circuit, biasing the pin diode. We want to ensure that the DC signal flows only towards the diode, not through the other line, because it is always the whole circuit is made of, if you see, it is actually the metallic connection, the microstrip line. So it can flow in either direction. No? We want to ensure that it only affects the diode only. And similarly, in the diode also, the diode biasing lines, we want to ensure the RF signal should not flow through that. So we need a choke or inductor, high inductor. So these components are required. Either you take a series switch or shunt switch. Okay, that is there. But now, what is the advantage of shunt switch? Why we need a different configuration at all? So what happens if you see in a series switch, the signal passes when the diode is on. But in the shunt case, when the diode is off, then the signal passes. When the diode is on, it gives a direct path to the ground. That's why the signal does not pass. So that is one condition. That is, by configuration only it is different. So what happens in the shunt is that the current does not depend. Here it is wrong. It will be does not depend on the resistance in the forward case. Obviously, because in the forward case, when you open the diode, that signal flows directly. Okay, there is no connection to ground, so it will have a very high power handling capacity. Okay, and another thing is, because if you just switch on the diode to block the device, it will go to ground, right? So it gives a very good isolation. The moment you put a sorting to the RF path, the almost whole signal passes to the ground. And this ground, you have to remember, this is not a DC ground. This ground, it should be to the RF ground. Okay, so that is why the RF signal will completely go to the ground. Okay, it will not pass to the other side or output side. So there are two advantages of shunt condition. One is it has a very high power handling capacity, and it has a very good isolation in the off case. Okay, when the signal does not pass through the circuit. So these are two advantages. Now it has a disadvantage also, because generally if you see, this is a normal schematic. If you see actually the implementation, you will need to have a λ/4 additional line to make it feasible. Okay, so the moment you add an additional line, it will reduce your bandwidth. Okay, because the matching happens only at a particular frequency, not at a side by a lot of other frequencies. So compared to the series switch, the bandwidth is less for a shunt switch. So obviously, there is a trade-off. Now, other possibilities is, instead of using pin diode, you can use a varactor or attenuator. All these are there, but pin diode also works fine. A simple pin diode with a good, intelligent design of your isolation circuit as well as your bias line. You can use it in a microstrip line for switching. So this, if you see, it represents your circuit, actual total circuit with choke as well as capacitor as well as biasing, everything together. See, in the series switch, what happens? You have these red plots, red lines. It shows your DC path. One will be used for biasing or DC VCC, and another is for ground. Okay, and you have a choke in both ways so that the RF signal does not pass through it. Choke is nothing but a high inductance. Okay. And you also have green resistance inductors, it is green capacitances that stops the DC biasing flows in that way. It goes only towards the diode. And similarly, you have the same thing in the shunt condition also. Okay, you have, but the biasing orientation is different here now. Okay, so now do you have any question here for a single SPST switch? How pin diode can be used here? That is what we have seen.
Shunt is for isolation.
Shunt is for isolation as well as for good power handling capacity. Yes.
Sir, we use inductor and capacitor for we use capacitor for DC blocking and inductor for RF blocking. So how we get the correct value for this inductor and capacitor? Like it is
Yes.
perfectly biased.
It is, you are saying how to calculate the capacitor inductor values?
Yeah, because we require it to be perfectly biased. Na? So for biasing,
See, generally we take very high values. Why? See, the capacitance, if you take, so capacitance, what is the reactance because of capacitance? 1 over j omega c, right? So if you increase the capacitance, it gives a, what happens? It reduces the signal, right?
yes.
Yes. So that means, yeah, if you increase it, the resistance, just a minute.
If we increase the capacitance, the total impedance will go to increase.
It will reduce, right?
Yeah.
Yeah. So yeah, so that means we don't want that. We want to then reduce, right? We want to increase the. Oh no, sorry. We see this capacitance. No, that's why the confusion. The capacitance we use for DC blocking, right? Not for RF blocking. So that means what the capacitance, whatever you put, the omega is 0 anyway. So it will give a very high impedance, right? It will give you a very high impedance anyway. That is okay. But the main part, you should consider is for the inductor. The inductor, what happens for the high impedance, for the high frequency, it should lead to very high impedance or high reactance, right? So again, for inductance, we have j omega L. So your omega is in the gigahertz range. Okay. So if your L is also high, then only your total impedance or j omega L should be high. Understand? Then only the RF frequency will not pass through that port. So generally, let's say you take a 100 nanohenry inductance, okay, for a gigahertz, 1 gigahertz signal.
Okay, so blocking the RF signal, we require higher inductor value, so it does not let the RF signal to pass through this. Correct?
Yes. We have to actually see. It is very simple circuit, okay? J omega L and 1 over j omega C. What do you actually want? One is for high frequency, one omega is very high, and another case omega is very less or zero.
Yes.
Ideally 0, right? That is how you calculate. Yes. This is nothing much engineering here. It is, but the engineering is mainly how you put this component, where you put the components. That is what makes it, effective as a switch.
I have a question. So
yes.
I have a question. See, the input capacitor is mainly to block the DC. Okay.
Right.
While selecting this component, whether this SFR of the component will also be taken into picture, self-resonant frequency of the component.
See, that's why I'm saying no. Because that will not put, will not matter much because your omega is almost 0, right? So that's why your 1 over j omega c you will go to almost infinite. Okay. So ideally, if you see, we generally put a around 50 picofarad capacitance and 100 nanohenry inductance. Okay. In this part.
In practical, we will use conical inductors and 100 puffs, sir.
Yes. You generally want to increase the values. Yes. Whatever is practically available, it will work. Yes. Capacitance is generally, it does not, there is no much stringent requirement on
Not
capacitance.
exactly, but inductor is main important here.
Yeah, inductor is mainly
100
important. Because your frequency is very high, right? So you want to increase that value there. You want to increase the resistance, reactance value, so that the signal does not flow. Okay, so we'll move to next now. Okay, so we have seen so far is SPST, single pole, single throw. Now, what is even more useful, if we get a SPDT switch, that means single pole, double throw. Okay, if you see these two combinations, here also we have two series and shunt, both the configurations possible. So what happens, you based on these two diodes, we will use two diodes here, we can have two defined combinations. Either it can connect to port 2 or port 3. Port 1, let's say, is the pole. Okay, now from here you can throw towards port 3 or you can throw towards port 3. 2 or 3 you can switch between. So that's why it's called SPDT switch. And if you see, there is, is similar, only you need two diodes. That means you need now two biasing circuits. Everything now increases. Okay. And now, but in the shunt condition, if you see, that is where actually it is important. Here you see, we have added additional line. This line length, additional line length in the shunt condition, in the right side, what we have is how much line, how much is the length required. Now, there is a very, what do you call fundamental difference between, analog switching or like low frequency switching and high frequency switching in our RF switching. Why? Because in the normal low frequency switching or, normal circuit board and all, what you don't have to consider is matching. But in our microstrip line, the moment you put the switches, it will affect the matching also. You have to take, everything now into consideration, because the diodes, it can make it as a open or short circuit, right, based on the diode switching or off switch on and off. Now if you see what we have seen in normal microstrip line, based on switch on and off, it can act like a inductor, capacitor, all these things will come. So the moment it happens, it will affect our matching, impedance matching of the circuit. So that is how our RF high frequency switching, you have to not only consider the diodes, you have to see if the matching is happening. You might as well get a very good switching, but you will see your signal is only not flowing because S11 is very poor. See, that is why you see in the series case, it does not affect much, because you can just make it like this, connect here. If you actually see, you have to consider yourself. Switch on either one and switch off the other. Okay, it might not affect. But if you see here in this case, in the our shunt combination, what happens? The moment you shunt the diode here, I told you, right, because this is not a DC grounding, this is RF grounding. If you shunt a diode, what happen? The signal will be also shunted to RF path. So that will change the effective impedance of the other portion also. Okay, now can you tell me why this, what length of this, additional length we should use in the shunt condition? So here you see how far away should this be from the junction in the shunt combination. When you switch on the diode, it is a RF grounding. Okay, so that means this junction is grounded. If you ground a junction, so that means you're here, this junction also, it will be grounded, right? So signal will not flow, only it has a RF path to ground, it will not flow. But so the whole circuit only will not act as a switch. So what can I do now?
Use a quarter wave line.
Yeah, why it will affect?
Yeah, like suppose we are grounding through the diode one path. So if we add a quarter wave line, it will like open, means like due to impedance inversion, we'll see open at the other end. So that path will be like
Yeah, right.
open.
You are very right. Yes. So generally, if you see from very basics of the transmission line, lambda by 4, if you traverse through a microstrip line, the characteristics changes completely oppositely. Open circuit becomes short circuit at that end, and short circuit becomes open circuit. Now, because it is shorted at this end, and at the lambda by 4 end here, it becomes open. So there is no effect of this circuit at all. Understand? So that's why the signal will completely flow from port 1 to port 3 here. But if you don't use this, the signal will be grounded in this junction. There will no signal flow through port 3, even though this diode does not, D2 does not have any effect. Only because of D1, it will have effect. So that's why in the shunt combination, we need a lambda by 4 additional line. Okay. So similarly, so you have to, whenever you design a switch, RF switch, you have to see for both your diode on and off 4 combinations, your matching is affected or not. Okay. So we'll see, this is taken from this Keysight application note. So this is the whole circuit, how it looks like. Okay. See, now it shows all the components of biasing, choke, capacitor, everything. And this, the circles here, it shows the ports. Port 1, 2, 3. Okay, 3 ports. And in between, this is the series. First one is the series combination, 2 diodes. And here it is the shunt combination. And here you see there's a lambda by 4 additional line in shunt. So yeah, look into this very carefully so you'll understand what I'm saying. Okay. How the biasing will affect everything. All right. So biasing has to be done carefully. You have choke and capacitor, as well as there is a lambda by 4 line to have the matching here. So this matching is affected mainly in the shunt combination, not in the switch single the series combination. And if you see here, so one simple example is that so this RF common port in the middle port here, let's say this here you connect a antenna. Okay. And this RF port this side and RF port 1 and 2, we can connect either transmitter or receiver. Now let's say you want to use this circuit switching for a radar or even communication both. So where you have a transmitting chain as well as receiving chain. And now you have a single antenna connected. By switching these two diodes, you can either connect to the transmit part or receive part. Okay, this is the simplest use of this. But you see how only 2 diodes or SPDT switch can make a whole chain feasible. Okay, this is a practical example. Okay, so okay, so we'll stop it here. Tomorrow we will look into the FET switch. Okay, FET switch and other case study applications and all. But yeah, do you have other doubts now in this part?
Once go back, one slide back.
Yeah, sure. Yes, here or here.
Here, once explain this one forward. This one, first one. Once explain this one, sir. Once.
Okay. See, it is don't get confused with seeing lot of circuits. So mainly the signal here RF port 1 to RF port 2 right side. It has to pass. Okay. And you have in between the RF port 3. Sorry, not from RF port 1 to 2. RF port 3 is the, let's say, incoming signal. It has to go to either port 1 or has to go to port 2. Okay. Single pole, double throw. Double throw is either 1 or 2. Now, how do we do it? You have to connect 2 switches in 2 paths. Okay. Now, for these 2 diodes, you need 2 biasing lines. So they have a common grounding in the middle and 2 bias 1 and bias 2, left side and right side 1. Now, for each biasing line, you see they have a inductor or RF choke, and they have a capacitor also. Okay. And in the common here, common ground, they have connected for the grounding of the DC. All right.
Yeah, okay.
Okay, yeah. So same case is here for the similar thing here for the shunt also shunt SPDT switch. Only thing is this lambda by 4 line is extra here. So just is what is seen here, shown here. Okay.
Once
Everything
go back.
is. Yes.
If you this one some previous slide only.
Okay.
No, another slide is there now. 2 block. Yes. Okay. This one only. If you want port 1 input, we are feeding input, sir.
No, sorry, not a port 1. We want to feed input through port 3. That is what I'm saying. A single port double throw. Let's take RF port 3.
Double throw. Okay.
RF port 3.
If you
yes.
Where we can our output will get. If you want to output at 1, which diode should on?
You are saying for the series case or shunt case?
No, if you feed RF at port 3,
No, that is, I understand. There is two, right? This top one is the switch and the bottom one is
top
the
one
shunt.
only, top one only I want, top one
Okay,
only.
okay. So let's say the
Okay.
top one case, you switch on the left side diode, okay, D1. Then what will happen? The signal will flow from port 3 towards port 1. And D2, let's say we switch off.
Okay.
Okay, so the signal will go to from port 3 to port 1, and there will be no signal at port 2. And it will be reverse. If we switch on D2 and switch off D1, signal from port 3 will flow towards port 2 only, will not go to port 1.
Okay.
Okay. And similarly, it will happen in the shunt condition also. Only the switch on and off will reverse. Okay. Just
okay.
go
Here
through
the
this.
isolation will not come here. At
Yeah,
port
see,
2
all
is
all the other things was told for the single pin diode. Everything is valid here. Only you need additional biasing lines. Okay, that's all. Nothing else is changing.
okay. Thank you.
Okay, so just I will ask you to go through this carefully, so you'll understand very well.
Sir, how to realize these switch on IC? Suppose I want to simulate the switch on some simulation point of view.
Yes. See, this is like you can actually do it, right? You just take, so there'll be models of diode. You can take it from datasheet. Just select some, Infineon or Skyworks. Go to pin diode
In
database.
IC format, sir.
IC format in the sense see, we are talking about microwave, right? So you have to do a microstrip line implementation. Microstrip line as well as a lumped component. That is what we are talking. But yeah, you can as well as do it, but I don't have expertise on that, I work in, or even this course is designed for, lumped components and all. IC obviously you can do, but yeah, I don't know about that.
Okay, not a problem.
Regarding the biasing, it is anode to cathode is been getting biased, right?
Anode to cathode will get biased. It's like, the forward biasing, right? You have to see in the forward biasing case, in the top one, the signal will flow, right? Yeah.
Right.
So that does depend on how you bias your ground and BCC, how it is placed. Okay. So here, if you see the ground is common, so you have to forward
Ground
bias
is
it. Yes.
So forward bias means it is just the old DC voltage applied.
Yes.
Right?
5 volt, let's say 3 volt applied. And if you give a 0 volt, it will be, reverse biased. Yes.
Reverse
Same
bias.
as normal
So
diode
it
circuit.
yeah, it is a normal diode where you anode to cathode, you apply DC voltage, and once after the application, you start to apply the RF signal from the port 3, and you take it at port 1, right?
Yes, right. Yes. So so the main thing is our port 3 is the signal. Okay, signal port, input port. It will go either to port 1 or port 2. Okay. Yes.
Depending upon the bias condition, which is going to turn on and turn off. Okay.
Right. Yes.
So here it is just a switch on, or it will be off state. It is
Off
not.
state,
It will not be in switching. It will not be in switching.
Yes, right. But another point you should note that even though we have two diodes, right, we don't have 4 defined combinations. Even with 2 diodes, we can have only 2 defined combination, either this side or that side. So that's why it is also called a 1-bit diode. Okay, it's not we don't have a 4 even though there are 2 diodes, it's not a 2-bit combination. Okay, we don't have. Yes.
What I thought is, if I if I apply the bias for the bias 1 and bias 2, I can make still diode D1 and D2 to conduct, right?
It can conduct, yes. Then the signal will flow through both of the parts.
Okay.
Not only that,
so
but see, not only that.
It will be divided, or it
one
will
minute.
be divided?
1 minute. I see. The problem is, signal you can divide whatever you want. But the moment you configure both of them to be on, then 250 ohms lines come in parallel. So what happens? What happens then in the junction?
It becomes
50 by
25.
2. Exactly. 25. Then what happens? Then the matching is completely gone. Signal will not flow only. Yeah, exactly. So that's why I'm saying you have to always see here Why you can't, do as you see in normal circuit switching? That will not here. You have to look into the matching also. Okay. Exactly. So all these combinations you
Okay.
see. So tomorrow we'll look into the phase shifter operation. With this, we will get only 1-bit phase shifter. Okay. Even though we have
Okay.
two diodes, you can, generally in our all circuits, digital circuits, we could get 2-bit condition. But no, it will work in the RF case only as a 1-bit phase shifter.
But here, when I give the input, and suppose if I turn on this and becomes 25 ohm, maybe not matched, the signal will be in phase or it will get out of phase.
So that will depend on the, RF. There is a equation, right? How much a signal is passing through that. That you can calculate from the equation. But the main condition is that, it's not only about, in phase or out of phase. The problem is the most of the signal will get reflected only from port 3. It will not pass only. Okay.
Okay. Thank
Yes.
you.
Yeah. Okay. Okay. So these are,
So
very,
last,
yeah.
I have
Okay.
one
Go.
question. So do we implement this on ADS, how, like which pin diode we have to use from which foundry, like you said, Infineon or?
Yeah. Actually, okay. Maybe I will see. This is very simple, even though it looks like complicated. It is not that complicated. You can do it. I am not going to show this one. I am going to show something else. Maybe I will show, share some paper with you so that you can do and learn yourself. Okay. Yeah.
Yeah. Yes. Okay. So thank you.
Okay. Okay. So we'll complete today's course here, and we'll meet you again tomorrow. Okay.
On this topic only, you will share paper, sir.
Yes. So that you can do yourself and learn.
Okay.
Okay.
Thank you.